Hi, today I want to talk about the Doppler effect. So what I want to draw is I want to draw a picture of what we just saw with that simulation. So like imagine if I had right here, I have a source. In the examples we've been talking about sound, but I also want to talk about light and see if we can take what we know about the Doppler effect with sound and apply it to what we know about the Doppler effect with light. So what I'm going to do is I am going to draw the waves coming up as best as I can. I'm not going to draw them in 3 dimensions, but I will draw them like this. This is when the source is stationary. So this source here is not moving. So because it's not moving, we get no Doppler effect. There you go. No Doppler effect if the source isn't moving. So now what I'm going to do is I'm going to draw the source, and we're just going to say it's moving with some kind of velocity in this direction. And what I would see is in front of it, I would see a compression of the sound waves. Those sound waves are closer together, and behind it, I would see those sound waves spread apart. And this would be an example of the Doppler effect. Now, if the source was moving with an even higher velocity, I would see more compression of the sound waves in front, and I would see more of what's called rarefaction. The waves in the back would be spread out further. So the faster you go, the more Doppler effect you see. So if they're stationary, you see no Doppler effect. If they're moving, you see some Doppler effect. And if they're really cooking, you're going to see a lot of Doppler effect. Well, all I've explained so far has to do with the waves. The wavelength is getting compressed. The waves are closer and closer together in the front, and the waves are spread apart in the back as this thing moves towards you and as this thing moves away from you. Well, really what you hear though is the frequency. You hear the pitch. So I have to talk about what's called the wave equation. And the wave equation looks a little something like this. This stands for velocity. That's the speed of the wave. How fast does the wave move? Not how fast does the ambulance move, if we're talking about an ambulance in the Doppler effect, but we're talking about a sound wave, if we're talking about sound or we're talking about light. So we got velocity. The F stands for frequency. Now, when we're talking about sound waves, frequency, another word for frequency is pitch or tone. What the frequency is the number of waves per second. That's how many waves hit you per second. That would be the frequency. And you would hear that for sound waves, you would hear that as a pitch or tone. This here, that funky looking symbol is the lowercase lambda. And I might be spelling this wrong, and I might be having some dyslexia right now, lambda. This stands for the wavelength. And the wavelength is the distance between waves. So if I was going to label that on my diagram, I would go over here and I would say that this is lambda. That's going to be the wavelength. And we can see that the wavelength is increasing in front, and the wavelength is decreasing in the front, and the wavelength is increasing in the back. And you can really see it down here. We're seeing a big increase in the rear behind it in the wavelength, and we're seeing a real decrease in the front as it moves towards us. So the wavelength is changing. And because the wavelength is changing, that ends up in a change in frequency. One thing that we have to understand about this, though, is that the velocity of the sound wave or the velocity of the light wave is constant. The velocity can't change. So when we're talking about velocity, we're talking about sound. Not the speed of the ambulance, but the speed of the sound wave. And I've got some information for you. So if we're talking about sound, The speed of sound is about 343 meters per second, which is also about 761 miles per hour. So the speed of sound is constant. That doesn't change. What changes is the speed of the ambulance. Speed of sound is constant. Another thing, if we're talking about light, well, the speed of light is also constant. That doesn't change either. And the speed of light is 3 times 10 to the 8th meters per second. The speed of light is also 1.86 times 10 to the 5th miles per second. And it is also 6.7 times 10 to the 8th miles in an hour. Light will travel 670 million miles in 1 hour. The point with this is that the velocity is constant. That is not what is changing. What's changing is the wavelength. Now, because the velocity is constant, I can say this. So, as the wavelength goes down, the frequency goes up. So, for the Doppler effect, the waves are getting squeezed together. And because the wavelength is going down, the frequency has to go up so that when you multiply those two numbers together, you get the speed of sound, because the speed of sound doesn't change. If I change the frequency, if I change the wavelength, the frequency has to change in the other way, inversely, it has to do the opposite, so that when I multiply those together, I still get the velocity of sound, which is constant. Also, if the wavelength goes up, the frequency goes down. And this is called the Doppler effect. This is the Doppler effect. There you have it. But that's how the Doppler affects for sound. Yes, ma'am, you can, Lexi. I'm almost done, though. I need to talk one last thing. Instead of an ambulance, imagine a star. Imagine that this is not an ambulance anymore. This is a star, and we're talking about light. We're talking about light. If the star is moving towards us, the frequency goes up. This is called blue shift. The light would be more blue. If the star is moving towards us, the light is more blue. If the star is moving away from us, that means the frequency is, wait, hold on. I made a mistake over here. This should be a down arrow. That should be a down arrow, because as the wavelength increases, the frequency goes down. And as the frequency goes down, if we're talking about light, we call this redshift. So if a star moves towards us, its light would be shifted into the blue. And if a star moves away from us, the light would be shifted into the red. We know that the universe is expanding because the light from these galaxies is shifted into the red. It's red shifted. That is the evidence for the Big Bang. That's how we know that the universe is expanding. Because when we look out into space, we see galaxies and we see the light from those galaxies, and we see that the light is shifted into the red. Almost every galaxy that we look at is redshifted. The further away a galaxy is, the more redshifted it is. That means it's moving even more quickly away from us. That means space is expanding even more when you get out to there. There are some galaxies that are coming towards us. There's one called the Andromeda Galaxy. It's the closest galaxy. It's our closest galactic neighbor. Those stars, that galaxy's light is blue shifted. That means that galaxy is actually moving towards our Milky Way galaxy. Eventually, those two galaxies are going to merge together. We can also use this Doppler effect to show that galaxies are rotating, Because if I look at one side of the galaxy, the stars are blue shifted. That means they're coming towards me. And if I look at the other side of the galaxy, the stars are red shifted. That means they're moving away from me. So when we talk about the answer to the question that I asked earlier today, how do we know the universe is expanding? We know that the universe is expanding because the light from galaxies is red shifted. And that means they're moving away from us. And that's how we use the Doppler effect to explain the expansion of the cosmos.